Hello, dears. How are you? Let's introduce together something known as vector space. So when you first hear the word vector, we think about something that has magnitude, and it has also a direction. So, and if we want to apply it to relate it to our major, which is engineering, and the physics courses that we are taking, or we can recall maybe the force, the velocity, and the acceleration, and these stuff. So in our mind, a vector, it means that it has a magnitude and it has a direction. But from linear algebra point of view, a vector, it's not necessary to be the vector that we know in the Euclidean space. The Euclidean space, we mean the vectors that they are like ij in R2, ijk in R cube, E1, E2, E3, E4 in R4, and so on. A vector space is a collection of elements. These elements, we will call them vectors, and it has two operations, addition and scalar multiplication. And it should be satisfying these conditions. The closure axioms, it means that if we're adding two elements inside the space, the result, it should be also inside the space. And the scalar multiplication also should stay. Also, the commutativity property. It means that if we're adding the first vector to the second, and someone in Australia is adding the second to the first, we should get the same answer. The associativity property, if we have more than two vectors, let's say we have three vectors, we need to add them, u plus v plus w. So if someone in UAE started by adding v plus w, and then she or he added u to it, and someone in USA started with u plus v and then added to it w, she or he will get the same answer as the one that is in UAE. One more thing, what do we need? We need something known as zero vector. The zero vector, from its name, it means that under addition, it doesn't affect the new vector. So if we're adding a certain vector to the zero vector, the result will be the other vector that we have. Also, we need the negative. So if we have a vector, we need the negative of this vector to be. What can we, or how can we understand the negative? Let's go back to real numbers. Let's say if we have a 2, we'll have a negative 2. So negative 2 plus 2 is equal to 0, right? But here it's not equal to the 0, the number that we know, it will be the 0 vector. Then we have these axioms for the multiplication axioms, and these ones, they remind us actually of real numbers. Okay, now, why do we need to learn vector spaces? Is it that abstract object, or does it have applications in real life? So about some computer applications, let's take the space of all possible colors that can be displayed on a computer screen. This is a vector space of colors. So our vectors, each color is a vector. Let's say the blue is a vector. The red is a vector. The purple is a vector also. So we need here two operations, the addition, and what do we need also? The scalar multiplication. And we need to identify our zero vector. So what's our zero vector that we're saying here? Our zero vector is the black. Now we know that the black exists when we have absence of light, right? This one, we have to highlight it because we'll go back again to it. Now, how addition of vector will happen? We are saying here that the addition, it works by adding any two colors and combining them in a certain proportion to create a new color. Like if we take the colors red and blue and add them together, we will get purple. It's again a color, right? And if we take the color blue and green, we will get also another color. Okay, this is regarding addition. What about scalar multiplication? So the scalar multiplication in this vector space works by taking a color and scaling its RGB values by a constant factor. So it means that here we are dealing with the lightness of it. If we take the RGB value to be very small, it will be very light. And if we take it to be a relatively high, it will be like darker a little bit. Okay, but finally, we should have, what should we have also? We should have a condition that when we add U to 0, we should get U, right? This one, this condition, it should be satisfied. Okay, remember, what's our zero factor? Our zero factor is the black, and the black is lack of color. So let's combine the black, let's say, with white. The black is the absence of light. We're adding it to white, so logically we should get white, right? Similarly, if we added it to red, purple, blue, and so on. So we can also check on this one, all these axioms, and finally we got a colorful vector space. Okay, miss. Now let's talk a little bit more mathematics and forget a little bit about colors. The vectors that we know, whenever we have a vector, we imagine this shape, whether in R square or R cube, and we generate it before to Rn. This Rn, it contains what? It's n tuples, right? It contains n entries, and we can put it in this way or put it as column, if you still remember. A1, A2 till An. Let's think a little bit about Rn addition of vectors. Do we still remember how to add two vectors? So all what we have to do is just go to the corresponding entries and add them, right? And what about the scalar multiplication? We will multiply each of these entries by the scalar. What's the zero vector in Rn? All the entries are zeros. So let's pause a little bit the video and go to the conditions of a vector space and check if Rn it satisfies these conditions. Okay, let's go to another space. What about polynomials? Polynomials, they are very important, right? So usually polynomials, when we talk about polynomials, that means that we need a degree for it. For example, x squared is a polynomial of degree 2. X power 100 minus 2x plus 5 is a polynomial of degree 100, and so on. How do we add two polynomials? We add usually the coefficients together. Let's say if we have x squared plus 5, we're adding it to 3x cubed, let's say, plus x squared minus 1. How do we add it? So we have x cubed, we'll write x cubed, we'll write x squared, and we have the constant. Do we have here an x cubed in the first one? No, so the coefficient is 0. Whereas in the second one, it's 3. So 3 plus 0 will get 3. Here we have x squared, and here we have x squared, so we'll add their coefficients, and here the constant is 5, and here the second one, the constant is -1, so we'll get this new polynomial. How do we multiply a polynomial by a scalar? So what should we do? We will multiply each entry, the coefficients by what, miss? By the scalar. Let's apply it to a certain example. Let's say we have 3x squared minus 5. What will we get? 3x squared minus 50. Okay, these are polynomials. So let's put this example. X squared plus 2 plus minus x squared plus 5. Okay, let's try to add these two polynomials. What will we get? We will get x squared minus x squared is 0 plus 7, right? This is our answer. Is it a polynomial of degree 2? It's not, right? It's a constant, so it's not a polynomial of degree 2. So what can we say about polynomial if we need a polynomial of degree 2 or of degree 3? The addition here is closed. Here we added two polynomials, but we did not get a polynomial of the same degree. So actually, it's not a vector space. So we'll define something else. We'll define Pn. Pn is the set of all polynomials of degree less than or equal to n. So if we have P2, means that it's anything that we have here, ax squared plus bx plus c. A, b, and c can be any real numbers, even they can be 0. So here, if we have x, it belongs to P2, although its degree is not 2, but it's less than or equal to 2. If we have 5, also it's an element in P2. In this case, this space of polynomials under addition and scalar multiplication, we will get it as a vector space. Also, again, try to pause the video a little bit, go to the axioms and check if they are satisfied. So P2, it has this shape. What if we want P3, miss? So if we want P3, it will be ax cubed plus bx squared plus cx plus d. P4, it means that ax4 plus bx cubed plus cx squared plus dx plus e. Okay. We still have a vector space that is very important that we already, our whole course is about it, matrices, right? Okay. So again, how do we add two matrices? If we add two matrices, let's say their size is 2 by 3, both of them, the result, it will be again 2 by 3. So there is closure here, right, under addition. And scalar multiplication doesn't affect the size of the matrix. So basically, it satisfies the condition of vector spaces. So also, this one is a vector space under the usual operation. So we have, these are our main vector spaces, Rn, the matrices, these are of size m by n, and the polynomials. The zero vector in Rn is 0, 0. How many times, miss? N times. The zero vector here is the zero matrix, that is the size of it is m by n, and in polynomials, the zero vector is 0, which we can write it as 0x power n plus 0x n minus 1 plus till we reach 0. Okay, here we have some properties. They should be holding in any vector space. The zero, number 0 times a vector, it should give us the zero vector. And a constant, any constant times the zero vector, we should get the zero vector. Okay, guys, I hope that you enjoyed this introduction. See you hopefully during the lecture to elaborate more. Have a great day.